Greetings, everybody. Welcome to the latest edition of the Physics Corner with your host, Dr. Christopher Sorolla. Today, we're taking a look at the speed of an electromagnetic wave. Now, this might be something you've already dealt with in lecture, but just in case, it's worth taking a second peek at here. What I want to do is both show what the units are for this and what the value of it is. And at the end of it, it might be a number that you have known about all along. So, let's take a peek at it. Now, we're not going to derive how you get here from scratch. That is basically a calculus-based idea at the very least to truly get to where you need to go. What we can do though here is state the result, that the speed of an electromagnetic wave in vacuum, we'll let it be v for now, is equal to 1 divided by the square root of these two constants. Remember what these constants are. There's the permeability of free space and a permittivity of free space. Permeability is for magnetism, basically how easy it is for magnetic fields to go through vacuum. And permittivity is equivalent for electricity, how easy is it for electric fields to travel through vacuum. So with those two things in mind, we can talk about the speed of an electromagnetic wave in vacuum. Okay. Now, by the way, the speed of electromagnetic wave in a material, that's a different question, and that's one you'll probably see in future videos and in future classes. Now, instead of trying to tackle it all at once because it's kind of jumbled up, I want to handle it in pieces. So let's take a look at the units part first, and then we'll actually plug in the numbers. So we're going to split it up a little bit because, as you can see from the units for both of these constants, they're pretty intricate. There's a lot going on there. And so we're going to need a little bit of attention just on the units alone to make sure that they work out the way they're supposed to work. But let's do that. So for the units specifically, what do we have? All right, so it's 1 divided by, so for mu naught, it is Teslas times meters per ampere. For epsilon naught, it is Coulomb squared divided by newtons times meters squared, like that. And of course, this whole thing is under a square root sign. Let's not forget that. And this looks pretty messy. So now there's several ways to go about this. There's no one particular way or even one optimal way to, say, analyze the units. But I thought it might be interesting or instructive at least to maybe take a simplest approach that we can think of for you folks right now. And that's to attack maybe the most difficult of the units to play with, and it's probably the Tesla. So what is the Tesla? Where does it come from? What kind of unit, where does it come from? Like many of the electrical units, the Tesla is a combination of many things. So if we can break down the Tesla into something a little bit more simple, we might be onto something. Now, having said that, meters are standard units. They're fundamental units in that you can't break them down to anything else. And so will be kilograms and seconds, and for that matter here, coulombs. Notice we've got also amperes and newtons at play. I'm looking ahead a little bit for me. I'm going to leave those alone for the moment. So how do I break down the Tesla? Well, let's bring in Faraday's law. Take a peek. And Faraday's law says this, that the EMF you generate is equal to the negative of a change of magnetic flux over time. Looks like that, right? So that's what Faraday's law talks about. What are the units then? The units on Faraday's law are volts, so capital V for volts over here, so that's an EMF, right? Over here, the change part doesn't matter. The change doesn't do anything to the units, but it is magnetic flux. Magnetic flux is a magnetic field through an area, right? So that would be Teslas multiplied by meters squared. And again, let's use all of our standard units. Don't mix and match, right? We wouldn't want to put in square centimeters, for example, at this stage. So stick with the standard units. And on the bottom, a change of time, well, time comes in seconds. So we have something that looks like that, all right? So if we take this, let's solve for Teslas here. The Tesla then is equal to what? Well, there's a volt. To get the Tesla isolated, multiply both sides by seconds and divide both sides by meters squared. So we have that, all right? So we can replace the Teslas here with this combination. Now again, it doesn't look like it's going to get us too far at first glance, but like I said before, let's tackle the most difficult, the weirdest, or the most intricate of these units first and see if it leads us somewhere useful. So let's go from here down to here, all right? So instead of Teslas, I now have volts times seconds per meter squared. Don't forget there's a meter and an ampere still here. And then there's a Coulomb squared and a Newton meter squared there. And again, all this is being divided by over 1 over that, excuse me, make sure I say that correctly, and a square root, so 1/2 like that. Now, what can we do next? Well, there's another interesting idea we've had for electric fields. Remember electric fields? From way back at the beginning of, say, this course, you had electric fields. Electric fields, the units, were originally told to you as newtons per meter. Excuse me, newtons per coulomb, sorry. Again, make sure I say these things correctly. Newtons per coulomb. But then we also found out in the next chapter, another way to say that was volts per meter. Wow, let's check out something. There's a volt and there's a meter. So if I isolate this volt and this meter, I can put in newtons per coulomb. Now, why would I want to do that? Because there's a coulomb and a newton here that I can maybe get rid of. Next thing, what about electric current? The units for electric current are amperes, but an ampere is really a coulomb per second, isn't it? Because the definition of electric current is a flow of charge per unit time. So an amp is really coulomb per second. All right. So next step. This volt and one of those meters, I'm going to take and put in a newton per coulomb instead. Now, let's be careful here. That means I leave behind this second, that wasn't part of it, and one of those meters. I only needed one of the meters for volts per meter, right? If you look carefully. So pick up one of those other meters there, like that. So volts times seconds per meter squared, I can rearrange like this. I have meters here. Then there's this ampere. It's 1 over amps, so if I flip this, it would be seconds per coulomb, like that, okay? Here's a coulomb squared that we left alone, and a newton and a meter squared we've also left alone, and again, whole thing is under a square root sign. Okay, now comes the payoff. So again, I must emphasize there's many ways to go about this particular task. You might even be able to find someone or find your own way of doing it in a simpler fashion. But I'm picking this one because it lets us do a little bit of review of some other formulas and some other concepts we've had before. All right, so before we do anything with the square root sign, let's see if we can simplify here. So newtons divided by newtons. Newtons go away. Coulombs times coulombs is coulomb squared. I'm dividing by coulomb squared. Coulomb squared multiply. So coulomb squared on top cancels coulomb squared on bottom like that. This meter cancels this meter. And let's take a look then. What I'm left with, seconds squared, right there and there, and meter squared here. So now, if I'm dividing by this quantity, I can just simply flip everybody, and I'll have meter squared per second squared to the 1/2 power, right? Which, of course, then is simply meters per second. So, again, many ways to do this, but this is the way I decided to do it. We can show that the units for this wild combination of items actually comes out to meters per second. So whatever number we calculate, it's going to come out meters per second, which is the units for velocity, right? So we get part where we want to go. All right, what about the number? Okay, so let's get back to the number part. And to show that off, let's rewrite the formula for that. Okay. Now, because I'm just doing the number, and this is a calculation you can perform on your calculator for yourselves, I'm just going to write in the numbers. We already did the units. We know the units will turn out to be correct. Let's write down what you'll have, though. So, mu naught is 4 pi times 10 to the negative 7th. epsilon naught was 8.854 multiplied by 10 to the negative 12th. And again, notice everything is still under a square root sign on the bottom. So when you plug all this into a calculator, my advice would be hit the number pi first, then multiply by 4 times 10 to the minus 7th, multiplied by this number here, 8.854 times 10 to the minus 12th. You'll get a very tiny number. Get that all together. Then take the square root. You still have kind of a tiny number. Last step, 1 divided by that. And most calculators do have a 1 to the over x button or a x to the minus 1 button in which you can perform that task. When you do this, and let me write down the answer that you get to 3 significant figures, this is what you have. This ought to look familiar. And again, this might be a thing that your professors helped you do in class. So if it's repeat, then that's fine. But check it out what we got. It's the speed of light. Now, to give you a real quick history bit on this, and I usually don't do this because we're usually focused on the calculation, but I wanted to do this. Way back when Maxwell was working on Maxwell's equations, when he was putting together the various equations and composing a set that showed how all of electricity and magnetism are related to each other and how they interact and whatnot, he put in some equations and did some fiddling with the math and created what we call a wave equation, which in other words shows that electric fields and magnetic fields combined together can form waves. Now, it doesn't specify that they're sine waves or what kind of wave they are. It just simply says they're waves in general. And then also come out of that is the speed of a wave. And this was the formula he had. Now, by that stage, researchers did have reasonable values for both of these constants. And he was able to then calculate a number that was pretty close to this. And again, by that stage, people had separately measured the speed of light reasonably accurately and realized that the speed of an electromagnetic wave is the speed of light. Or light, and let's write this conclusion down, light, visible light, is an electromagnetic wave. That's the conclusion. That's what it means, which is something pretty profound. Now, we're used to growing up with that these days, but back then that was brand new knowledge. That was a new thing, and that was a pretty big advance. There's a fair case to be made, real quick statement here, between, say, Newton and Einstein, which of course are the two most famous brainy physicists you'll ever hear about in everyday life. Who would have fit between them as like the smartest person around? That would have been James Clerk Maxwell. Pretty strong argument you can make that. And here's one of the reasons why. All right, so support staff is Sidney Gautran and Sophia Turner. So funding for our program comes from the University of Mississippi and University of Southern Mississippi. As always, I'm your host, Dr. Christopher Sorolla, broadcasting from Hattiesburg, Mississippi. Thanking everybody for your attention and clear skies.